Hello and welcome. So we're going to be talking about trigonometric ratios and their inverses today. So just a reminder on some important things we're going to need to know. SOHCAHTOA is the acronym for remembering the ratios for sine, cosine, and tangent. Remember, sine is the opposite to hypotenuse, cosine the adjacent to hypotenuse, and tangent the opposite to adjacent from some reference angle, which is theta in this particular case. When we say opposite, we're talking about all the way across the triangle on the opposite side. That is the opposite leg to theta. Adjacent means right next to, so if it's right next to theta, that's the adjacent leg. And the hypotenuse is always the hypotenuse across from your right angle. Okay, so first let's talk about using calculators to evaluate trig functions. So there's two ways you can do it. You can do it in degrees or in radians. This particular lesson will only use degrees. So when you're using your calculator, just keep in mind that you have your sine, cosine, tangent buttons, usually for most scientific calculators, but you'll see there's this little slider above the number pad. I'm kind of changing between two modes there, RAD and DEG. RAD stands for radians, DEG for degrees. So make sure that your calculator, whatever you are using, is in degree mode. Otherwise, you won't be able to get any of these other answers. All right, so for this one, if I wanted to find the sine of 32 degrees, sine 32, I don't need the degree symbol because I'm in degree mode, right? It's assuming that's a degree for me. And then there's my answer. It literally tells me that sine of 32 degrees is 0.5299. If I wanted to round that to third decimal place, that fourth digit of 9 would round up. So this is approximately 0.530. And there you go. That's all you need to do for that one. Tangent is 65 degrees, same thing, right? We would say tangent button, 65, so 2.145 would be your answer. So approximately 2.145. Okay. Now, the inverse functions are a little more interesting. So this tells me what function to use, right? And this is your angle. And what we get is a ratio or a value, right? So we said sine function of an angle equals a ratio or value. And that's what we just evaluated. Now, inverses undo that, where this is the ratio, forgot the T, equals the angle, meaning inverses find angles, right? So trig inverses find angles. If you need an angle, you're going to use a trig inverse to find it. All right. So for example, that cosine to the -1 generally is going to be either above your cosine button or in this particular Desmos calculator, it's in the function tab, right? And then you say square root 2 divided by 2. So that's the ratio from the triangle, and when I put it in, it gives me back an angle. And because I'm in degree mode, that's 45 degrees is coming back as my answer, right? So equals 45 degrees. That means that when you have a cosine value of 45 degrees, the value that you will get is root 2 over 2. It's just going the other direction. Now, this is going to be an interesting case. Now, reminder, for any angle, sine is the opposite over the hypotenuse. So 4 would be the opposite leg, 3 is the hypotenuse. Now, hopefully, as I wrote that out, that kind of had some warning bells for you. Is it possible for the leg to be longer than the hypotenuse? No. And this is where we have to be a little careful with trig inverses, is that you will only be able to find trig inverses for sine and cosine for values that are between -1 and 1. 4/3 is larger than 1, which means that angle does not exist. There is no angle that would give you a value larger than 1. All right? The tangent function doesn't have those restrictions, but sine, cosine do. Keep that in mind. All right, so to solve any of these, the first thing you want to figure out is what are you given? So for this first triangle, we're given an angle, a side, and a side, right? The first side, RA, is the opposite to the angle that we're given, right? The 13 is the hypotenuse. That is always your first step. Identify what you have and what parts of the triangle it's at. And then you have your three functions, sine, cosine, and tangent. Which function uses an opposite in hypotenuse? Well, that's going to be the sine function. And then you literally create that ratio. You say sine of your angle equals the ratio? Well, our angle is 19. Our ratio is opposite over hypotenuse, a over 13. And then once that's set up, your goal is to find your only unknown, which is a in this case. That's our variable. So our goal is a equals. Well, I could care less about doing or undoing that, right? My goal is to get a alone, and it's tied to 13. Well, we undo division of 13 with multiplication, so multiply 13 both sides, which means a equals 13 times the sine of 19 degrees. That is the exact answer. Now, typically, we don't really care about the exact answer as much, so 13 sine of 19 degrees, we want the approximate. Put it into your calculator. Typically, second or third decimal place, I'm just going to go third. Nope, doesn't state. So I'm going to say third decimal place. So 4.232 will be my answer. All right, that is the approximation of 13 times the sine of 19, and that's it. That's as much as this needs to go. Right? And it's literally just going to be rinse and repeat for that one. Now, B is going to be a little more challenging, but not by much. So first off, we have an angle. It's theta, right? We have 47 and 186 given to us. So 47 is the side that's opposite to theta. 186 is the side that is adjacent to theta, right? And then this is our angle over here in the corner. So I'd say, all right, which function uses opposite and adjacent? Well, that's tangent. So my setup is going to be tangent of an angle equals a ratio. Always going to be setting it up that way, right? Our angle, we don't know. That is our theta. The opposite, we know, is 47. The adjacent, 186. And what's our only variable here? Well, it's the only thing we don't know. That is theta, right? Your goal, end goal for this one will be theta equals. And you're like, okay, well, that's nice. How on earth do I get tangent away from theta? Because that is not multiplication there. That is not being multiplied. It's an operation. Tangent is an operation on the angle. So you think, okay, well, if I have addition, we undo that with subtraction. We undo division with multiplication. I undo something squared with the square root. Well, if I need to undo a tangent, we use its inverse. So all I need to do is take the inverse tangent of the left side. And what I do to the left, you do to the right. Right? Just like how subtraction undoes addition and everything else for those inverse operations, inverse tangent undoes tangent. So what ends up happening is that those will end up canceling and your theta will come out and be by itself. Right? We undid the tangent. So theta equals the inverse tangent of 47 1/86. And there you go. You solved for theta. That's the exact answer. So all we do now is we just need to find that. So we have 47 over 186, inverse tangent of that, and we get 14.181 degrees. And there's your angle. Right, is 14.181 degrees is the angle that would create that particular triangle. Okay, that's honestly as crazy as it gets. The rest of these examples, we'll just be doing a lot of those exact same setups. So we're going to move a little bit faster now. All right, so example 3, find the indicated side or angle. So here's our angle, side, side. We have the adjacent side and the hypotenuse, which will be cosine. So cosine of an angle equals a ratio. Our angle is 55. Our adjacent, 20, hypotenuse, x. And then it's just a matter of solving, right? We undo division with multiplication, right? I want to get my x alone, so having it in the denominator is not helpful. Then we have x times the cosine of 55 degrees equals 20. Well, we undo that multiplication with x and cosine by dividing. Now, it may look a little weird to write it this way, but we have the same thing over the same thing. That is in essence 1, so that cancels and leaves you with just x. So x equals 20 over the cosine of 55 degrees. And there you go. Like once you solve for that variable, you are done. You're finished. All you have to do is just plug it in, and and find that decimal approximation. So 34.869. Right? I don't need a degree symbol because I didn't use an inverse. Right? I'm not solving for an angle. That x was standing in for a length. So there is my answer. I don't know what the length was, so I'm not going to put units. Okay, and there we go. Next one, we have example B. So we have angle 11 and 12. So from our angle, 11 is the opposite side, 12 is hypotenuse. This is a sine function. Right? Our opposite is 11, hypotenuse 12. Our angle, our theta, is unknown, so that is my goal. Right? So theta equals end goal. So here, same thing. It's attached by sine, right? Theta is attached to sine, so we have to undo sine. Only way to undo that is with its inverse. And what I do to one side, I do to the other, right? Those undo each other and leave you with just theta. So theta equals inverse sine of 11/12. Solve for theta, you're good to go, right? And then this goes straight into your calculator. So we have inverse sine of 11/12, and 66.444 will be our answer. Right? We solved for an angle. We were in degree mode, so that should be 66.444 degrees. Right? We actually do know that one, so make sure we write it that way. Okay, not too shabby. 2 more left to go. So example C, we have theta, we have 14, and we have 5. 14 is the adjacent, 5 is the opposite. The only function that uses opposite and adjacent is our tangent. Now, I didn't mention this earlier, but the reason why we're using sine, cosine, and tangent and not secant, cosecant, or cotangent is because we don't have buttons for those reciprocal functions. We only have buttons for sine, cosine, tangent, which is why those are the ones we're using. So just as a heads up on that, quick mention. So the opposite's 5, adjacent is 14. Angle, we don't know. Right? Undo tangent to get to the angle by using its inverse function. So I'm going to move that off to the side. Inverse tangent. There we go. So those undo each other, and you're left with theta equals the inverse tangent of 5/14. You've solved for theta. You are done, right? All we have to do is just plug that in. So inverse tangent, 5/14. We're in degree mode, which means that we have 654 degrees. Final answer, you're done. Okay? Now, probably as crazy as something like this will ever end up getting for you is something like example D, where here we have 3 unknowns. We don't know z, x, or y. But there is a couple of things that could make our life easier. We could actually do 3 separate setups for angles. 3 separate ratios for our 2 angles and side. We could absolutely do that. But also, don't forget the basic things you know about right triangles as well, right? If you know you have a right triangle and you know 2 out of the 3 sides on the right triangle, wink, wink, you know, or you should know, a theorem that tells you that third side. It's called the Pythagorean theorem, right? If you know 2 out of the 3 sides of a right triangle, you can use Pythagorean theorem to find the third. Or you can use a trig ratio. Either works. I personally like using Pythagorean theorem, so that's what I'm going to do. So Pythagorean theorem states that you have one of the legs squared plus one of the other legs squared. So 6 squared plus y squared equals the hypotenuse, which is 11 squared. Ta-da! All right, so we have 36 plus y squared equals 121. Subtract that 36 on both sides, so then we have 121 minus 36, and that will give us 85. So y squared equals 85, right? We undo squares with square roots. Now, technically you have plus minus, But we're talking lengths here. It wouldn't make sense to have a negative length. So you're just going to have y equals square root of 85. Now 85 is the same thing as 5 times 17. That square root is not going to simplify, so that is as good as it gets. Okay. Now on this one, until you're at the final answer, I wouldn't recommend getting decimals. So I'm going to leave that as that square root of 85 for a hot minute. So instead of y, I know that is the square root of 85. And now I can leisurely pick my next variable to solve for. It doesn't matter which one I want, like which one you use, you just need to solve for one of them, right? I like x, so let's use this as my angle. So if I'm solving for x, let's use whole numbers that are much nicer to use than worrying about square roots. So that would then be the adjacent and the hypotenuse. So that will be a cosine function. So cosine of your angle equals the ratio adjacent over hypotenuse, so 6/11. And then undo cosine with its inverse. All right, so I'm going to take inverse cosine of both sides. All right, and you get x equals the inverse cosine of 6/11. And then this just goes right into the calculator. So we have inverse cosine 6/11. Right? And then from there you have 56.944 degrees. So x equals 56.944 degrees. There we go. Now on this one we can set up another trig ratio for z, right? You can use z with the opposite in hypotenuse. That could use a sine function to solve for z. But also we now know 2 out of the 3 angles, don't we? And don't all angles in a triangle add up to 180 degrees? They sure do, meaning that all we need to do to find z is we can actually just take our 180 and subtract the 90 degrees, that right angle, and the value we have for x, which we just so happen to have found, and we'll find our last answer. All right? Now I would recommend don't use the rounded value. It actually won't matter here because we're working with just one last calculation and subtraction. But it wouldn't hurt to use the whole thing. So 33.056 will be the value of z. Equals 33.056. And now, since we're at the very end, I'm going to get that decimal for y as well. So we have the square root of 85, so 9.220, because that 5 is that 4th digit we'll round up. So 9. There we go. 9.220. So there's our y. Our z, oops, is in degrees. Forgot to put that little symbol there. And then we also have our x. So even if you have 3 unknowns, it's still the exact same process, but you can also do a few easier tricks to help your life go a lot faster. All right, and that's as crazy as it gets. Thanks for watching.